Hello, my name is Emily Dunn, and today I will be presenting my project, Bimodal Microstructures and Nickel-Based Single Crystal Superalloys Subjected to Non-Isothermal Loading via Phase Field Method. I would like to thank the Texas A&M Online REU program for sponsoring this project, and would also like to acknowledge and express my appreciation for my mentors, Dr. Jean-Baruch Legraveron and Jose Dominic. Let us begin. Let's begin with a bit of background on the material I've been studying. Superalloys are metallic combinations favored for their performance in high-temperature environments. The focus of this project was on nickel-based superalloys, as these alloys are useful for jet engines and other high-temperature combustion engines. Such applications are the focus of the Extreme Environments Materials Lab, which this project was done in collaboration with. This project focused on studying the evolution of the microstructure in a nickel-based superalloy undergoing heat treatment at 1,273 degrees Kelvin and subsequent cooling at 950 degrees Kelvin. Modeling the microstructure at these temperatures allows us to determine how the nickel superalloy will behave at in-surface temperatures. This behavior refers to the nickel-based superalloy's thermomechanical properties. The microstructure gives us insight to these properties. Because at this very small scale, we can see how the structure would facilitate or hinder the motion of dislocations, which are line-shaped defects in a metal. Dislocations can both decrease and increase the strength of an alloy, depending on how they move through the metal while undergoing external forces like heat or stress. Based on the result of Boisonneau et al., we expect the heat treatment at 1,273 degrees Kelvin will result in these larger, non-uniform precipitates called secondary precipitates, and the cooling at 950 degrees Kelvin will result in the smaller, more uniform precipitates called tertiary precipitates. The two precipitates entail a bimodal microstructure, which would hinder the propagation of dislocations and strengthen the superalloy. They use a phase field model, providing a template for this project, but presumably through developing their own algorithm, which would be more time-consuming and complex to create. The primary focus of this project was to recreate the results of Boisonneau et al. Using a phase field method within the MOOS finite element framework. Using MOOS has the advantage of being able to develop simulations without a strong computer science background, as would be necessary for the previously described model. Phase field modeling entails using governing free energy equations and relevant material constraints to determine where in a material certain phases will evolve with time. In our case, the phase is determined by the concentration of aluminum as a percent. In terms of the results of Boisonneau et al., there is a matrix or background shown in black, which represents the gamma phase. Before heat treatment, the nickel-based superalloy is only in this phase, which according to Boisonneau et al. Corresponds to an aluminum concentration of 25%. After heat treatment, there is the existence of secondary precipitates, where a different phase appears as the concentration of aluminum is about 14%. Interestingly, in the Boisonneau et al. Model, the smaller tertiary precipitates are the same composition as the secondary precipitates. In phase field modeling with MOOS, it should not be complicated to describe these tertiary precipitates with a different composition. This is of interest as it has been experimentally verified that the secondary and tertiary precipitates are composed of different concentrations of aluminum. As mentioned in the previous slide, the simulation was made with an open-source finite element framework, MOOS, that has an existing phase field module. The simulations were run using high-performance research computing with Texas A&M, and the results are visualized with the MOOS recommended software, ParaView. To the right is a flowchart for the plan of this project. The objective of the preliminary modeling phase was to study the phase field capabilities of MOOS and the process of developing objects for the software, as well as translate the equations that describe the evolution of the concentration field, and thus the microstructure, into objects that drive the simulation. The 2D simulation phase describes developing custom objects as needed to improve the accuracy of the preliminary models, and to analyze the results of these 2D models, comparing them to the expected results from Boisonneau et al. This phase proved to be more complex than anticipated, as MOOS frequently undergoes updates, phasing out certain modules and objects. This proved to be challenging when primarily using existing non-custom objects. With more time, the further analysis phase would be explored. This entails exploring simulations with differing compositions between the secondary and tertiary precipitates, and creating a 3D version of the simulation to explore the shape and precipitates in a more realistic model. As described in the preliminary modeling phase, an important task of this project was mapping the governing equations to existing MOOS objects. The following table illustrates how governing equations described by Boisonneau et al. Are reflected in MOOS phase field simulations. First is the Cahn-Hilliard equation, which gives the time derivative of local concentration field. The concentration field determines the volume fraction of aluminum in nickel-aluminum superalloys and separates the precipitate phases from the matrix phase. Here, mobility, denoted m, gives the diffusivity of the interface, and the last term of the equation gives equilibrium fluctuations. The DFDC term is the derivative of total free energy with respect to the concentration field. The total free energy has three components shown below the Cahn-Hilliard equation. The homogeneous free energy component determines which phase will form over time at a certain position. It is a simple function of the local concentration field, the concentration field for the matrix phase, and the concentration field for the precipitate phase. It is also multiplied by an energy scaling term, mu. The heterogeneous free energy component serves as the gradient energy component and defines the behavior and sharpness of the precipitate interfaces. It is the gradient of the concentration field squared multiplied by a stiffness parameter. Lastly, the elastic energy component determines the shape and pattern of the precipitates, as the model will aim to minimize elastic stress by settling into a specific pattern. This is the sum of positive elastic stress and negative eigenstrain, which results from a lattice misfit term that will give a secondary precipitates with a cuboidal structure. Here's the simulation I have thus far. To the left is after 1700 seconds, and the right is after 25,000 seconds. The blue matrix represents a concentration of 22% aluminum, where the red precipitates have a higher concentration of 82% aluminum. This is not yet representing the gamma and gamma prime phases. This model shows the evolution of a concentration variable based on the minimization of free energy. It does not yet incorporate the solid mechanics module of Moose, which accounts for the elastic energy contribution. This model has also not yet been parameterized by temperature to be non-isothermal, and thus there is only uniform secondary precipitates. Though it is not the full result as achieved by Boisneau et al., it is a step in the right direction to producing a bimodal microstructure using phase field methods. Due to this model being governed by minimizing free energy, it rounds out with time. The cuboidal structure in future simulations will result from the negative lattice parameter in the eigenstrain. This will be incorporated with other solid mechanics parameters. Assuming later simulations will achieve a bimodal microstructure, it is important to consider how this describes the properties of the nickel-based superalloy. The existence of a bimodal microstructure, that is, having both larger anisotropic secondary precipitates and smaller uniform tertiary precipitates, predicts that the nickel-based superalloy will perform well against heat and stress, because the precipitates will hinder the motion of dislocations through the metal. The GIF on the right shows the propagation of a dislocation. The expected bimodal microstructure would have both large and small precipitates blocking such a motion in the nickel-based superalloy. The different compositions of the secondary and tertiary precipitates should still predict a strong nickel-based superalloy, as there would still be the existence of a bimodal microstructure. However, if the precipitates evolve to be particularly different in size or shape from the Boisneau et al. Model, this could predict different thermomechanical properties and describe the nickel-based superalloy differently. Other implications of similar models could be determining the optimal heat treatment and/or quenching temperature for a nickel-based superalloy for specific aircraft engines. Though less exhaustive and needing to have programming skills and needing to develop your own framework for a simulation, the Moose finite element framework still proved to be challenging. In future work with this software, I will likely rely more on custom objects I've developed myself. The simulation results thus far have shown that the framework can be used for an isothermal phase field model of a nickel-based superalloy, and the existing solid mechanics module is very promising for introducing elastic energy considerations to the model. After this is added, the descriptions of the different phases will be changed to be temperature dependent, hopefully yielding the same results as Boisneau et al. Then, the third phase of this project may be achieved, further exploring the implications of precipitate composition in 3D models as I plan to continue working with the Extreme Environment Materials Lab. I have been very grateful for the mentorship I have received from them. Finally, I would like to acknowledge these helpful references in my work thus far. Thank you.